Good morning. Welcome to this session. It's an honor for me to introduce this session's plenary speaker, Professor Whittingham. Professor Whittingham is a State University of New York Distinguished Professor of Chemistry and Material Science and Engineering at Binghamton and the 2019 Chemistry Nobel Laureate. He received his BA and PhD degrees in chemistry from Oxford University, where he is now an honorary fellow of New College. In 1972, he joined Exxon and discovered the role of intercalation in battery materials, which resulted in the first lithium rechargeable batteries that were built by Exxon Enterprises. He returned to academia, back to State University of New York, Binghamton in 1988 to initiate a program in materials chemistry. In 2018, he was elected a member of the National Academy of Engineering and received the prestigious Turnbull Award from MRS. Today, he's going to talk to us on the title, The Critical Role of Storage for Renewable Energy and Climate Change. So without further ado, I would like to pass the stage to Professor Whittingham.
Thank you very much, and you can hear me, I hope. What I'd like to do is give the big picture first, then get into details. So as we get more and more renewable energy, which is intermittent, we're going to have to store it. And I've shown you a few examples of storage here. The large lithium-ion facility, California. This is the largest facility in the world. But we always have to remember the best, or at least the very largest means of storing electrical energy is by pumped hydro. And there are many, many facilities like this around the world, and they take up about 90% of the storage. And you all have phones or similar devices, all of which use lithium-ion batteries. So when the Nobel Prize was announced, the Nobel Committee said that we had laid the foundation of a wireless fossil fuel society. What we have to do now is take action to help solve some of the world's challenges. But let me just show you some of the issues we have. Climate change is a lot of global messing up, a lot of disruption. And these are just slides within, I think, the last 6 months. In Kentucky, at the bottom there, in the glacier in Banff National Park in Canada. This used to be full of glaciers 10, 15 years ago. It's retreated totally. The top fire here is in Chile, and the lower one is the very recent one in Colorado in the United States. So this global messing up is impacting all of us, and it's only going to get worse. So let's just look up at a few issues. Climate change is going to happen. We are going to have to adapt to it, I think. I don't think there's any way of rolling it back. What we can do is prevent it getting worse and worse over time. So the first thing we have to do, we have to be willing to live with less fossil fuels. I'm not saying none, because I think there's certain things like aircraft, we're always going to use fossil fuels. So clean electrical energy will be the future. The major sources of that we're all familiar with are solar and wind. As I say, they are intermittent. Let's not forget also a lot of countries have a lot of hydropower, which is renewable, and some countries are now using tidal energy. So we have to use storage. Lithium batteries are the dominant form of portable storage by far at this point. And when we talk about storage, we're talking about both the transportation sector and the electrical grid. So I'm predicting that within 10, even sooner, major cities such as Singapore will ban the sale of internal combustion engine vehicles and maybe ban their use totally. Somewhere like Singapore, an island state, travel is not very long distance. It's relatively easy to do. Your lifetimes, autonomous vehicles become the norm. So you will not have to own your own vehicle. You will not have to charge it put it in a garage. You'll pull out your iPhone, hit a button, and the vehicle will drive itself to your front door. The other thing that renewable energy will give us cleaner electrical grid. And if we look at these two combined together, if we have a very good batteries in our vehicles, then we will be able to link these together to make a more resilient grid. And I'll get into that a little later on. But we need to tie everything together and not. But we have a number of sustainability challenges. It takes 50 to 80 kilowatt hours of energy to make a 1 battery. Long term, this is not a viable. Quite a lot of this is due to transportation of the various materials. Going from the mine to the finished, some materials may travel 30 to 50,000 miles. So we really need to do more at the source. And this also gives the countries where the mines are value added. They won't just be shipping the ore off to 2 or 3 other countries. Batteries are made. This ties down to really the issue if we're going to solve part of the sustainability issue and at the same time make the whole system more secure is to go away from the present global supply chain. Over the last decade, we've gone too global. We've got to pull it back somewhat and allow it to spread more. So each region in the world really needs to have its own supply chain, its own infrastructure. So cut down the trend. We as scientists really need to eliminate the critical elements or other devices. As an example, in batteries, cobalt has to go. It's too expensive. Really, the only place it comes from is Congo, and there's a lot of child labor and other issues based there. And things like graphite, nickel need to be sourced more locally. And Singapore has a great opportunity. You have the weather there that electric vehicles like. So you could easily be a model clean city for the world with only electric vehicles. But before we get totally electric and totally clean grid, challenges, both the mining and the processing of the materials need much cleaner technologies, and we need to work on doing that. So let me just show you what lithium-ion batteries are. Now I'll show you a number of examples here. Renewable energy, the sun and the wind farms in West Virginia. This is a 32 megawatt hour battery facility. It shifts the load and smooths the power. Then I show you a whole range of vehicles, from the little two-wheeler in Bermuda all the way to large trucks and these Mercedes buses you'll see in Europe. So electric vehicles are taking over little by little, and there's now far many options. The red car here is and the green one is a BMW. So the major automakers are now getting into the business. So, but let me, before I get into the challenges and opportunities, let me very briefly mention what a lithium battery is and what it isn't. So lithium batteries are circulation. What we mean by that, if you look at the little green ions here, are inserted within the crystalline lattice. In case graphite is the cathode, it's normally a lead compound. Originally, this was TiS2. It's now a range of materials, but particularly oxides. So the lithium ions go in and out of these materials. So they shuttle when fully charged in the anode. They move through the electrolyte into the cathode. And I'll show you in a moment why we do not have any lithium metal in these batteries. Okay. Little bit of history here. Back at Exxon in 1970s, we used pure lithium metal. It tends to form dendrites. These are spiky protuberances that go across the cell and short it out. So Exxon pretty quickly switched to lithium aluminum. which works well for maybe 50 charges. But it was Akira Yoshino who discovered that various carbons with a graphitic phase could store the lithium, and that's what I actually show you here. But the challenge is 2 grams of carbon to store 7 grams of lithium, and the carbon, in fact, takes up half the. So we want higher energy density systems, we've got to get rid of most of the carbon. The present approach here is to look at tin or silicon. Both of these react with more than 4 lithium ions each. So their volumetric energy density is essentially the same as lithium. And the holy grail is to go back to the lithium metal itself. Side, we started with the layered compound TiS2. John Goodenough was working on cobalt oxides, their magnetic behavior, and recognized they had the same structure. So he looked at their electrochemical behavior, and you all know the history. All your cell phones are basically still lithium cobalt oxide. I mentioned earlier, cobalt is too expensive. Same structure is now made up of nickel, manganese, and a little bit of cobalt, and a little bit of aluminum. But there's a lot of interest now in going away from these expensive metals to lower cost and safer, such as iron phosphate. But these have a lower energy density. And so we and others now looking at, can we in fact put 2 lithiums into these phosphates to make them behave more like lead oxides and have the same energy density? So don't we use lithium? This is why, and this is a study that Russ Kennelly did at Exxon about 1975. When you charge a battery, you're electroplating lithium out. So you got one electrode on this side, this one. As soon as you got these little protuberances formed, and the electrical field between this tip and the other side is higher, so they then grow exponentially. So the difficulty in lithium batteries is to straight to the normal separator. If they do that, then you have fires, as of this case AT&T had in Texas. So that's why lithium is not really used anymore in batteries. There is one exception, but otherwise they're just not used. So if we go back to our TiS2, why was titanium sulfide looked at? It gives almost a perfect cathode. It's really the model compound, except its energy density isn't all that high. It's a metallic conductor, so you don't need to mix any carbon with it, because you've got to remember, in an electrochemical cell, you're moving lithium ions, you're also moving electrons. So you've got to make sure in and out. And this is data from back in 1973, run at 10 milliamps. This is about 5 to 10 times what you use today. Commercial operators also like the fact that in these materials, it is slightly slopey. Being slightly slopey, it means that the essentially got what you can call a gas, full or empty you are. Okay. I needn't address the fact that it's layered and there's no phase transition in here. I should point that out. So it's a single phase all the way from 0 to 1 lithium, sending any energy, nucleating a new phase. It's still very much of interest, TiS2. So Linda Nazar in Canada found out that magnesium would go in and out of this material very readily. And you can see the sloping behavior is almost identical to lithium. The big difference is it's about 1 volt lower. It's operated at an elevated temperature as compared with room temperature for the lithium case, and the current density is much lower. So TiS2 is a because the lithium energy density is twice that of magnesium. So magnesium, good model area, but not realistic for commercial application. So if we look at today's batteries, no, how do they stand? Can we improve them or not? And if you just look at the data, the percentage number there is the percentage of the theoretical energy density that we actually get in real cells. And you can see it's a tiny fraction, 11% to 25%. On a volumetric basis, it's percent on the gravimetric. So it's still a huge opportunity to increase that energy density. And we believe we should be able to at least double that. But it means we've got to take out most of the carbon. We need to put more lithium in there. And ideally, we need to do science on our materials to make them better ionic and electric. If we can do that, then we can use thicker electrodes so we can eliminate part of the dead weight from current collectors and the separators. So let me just show you where we stand right now and what we're trying to do. So initially in these layered oxides, there was equal amounts of nickel, manganese, and cobalt. That's shown up here. This has the highest thermal stability. So all these layered oxides are metastable. If you heat them up after they've been charged, they will evolve oxygen. Then there's an internal source to burn the battery, so one have to be very careful. So this is the safest one, but its capacity is only 160. If you go to more than 80% nickel, you can get well over 200, but then its thermal stability is 100 degrees lower. This is trade-off between energy and safety, and I should emphasize we never expect to get to these temperatures, but this thermal stability is a direct measure of how reactive these materials are with the organic electrolytes. And I show on here, this is where you want to get to 100% capacity retention and the highest energy. And you can plot this peak oxygen versus the nickel content, and it's essentially a straight line, independent of how fully charged the system is. So what we have to do is really modify these systems so we can increase the energy density, eliminate any of the side reactions, stop this oxygen evolution. And we're doing this through what is called a Battery 500 Consortium run by the Department of Energy in the United States out of Pacific Northwest National Lab. And this is a typical layered oxide. It's what we call the 100. The secondary particles, these are about 10 microns across. They pack very well to make a dense cathode. What we've been able to do over the last 5 years is increase their lifetime, increase their energy density, and at the same time, the commercial cells are coming down in cost. But as I say, there are issues with the safety here. So this is the data. This is an ex-PhD student of mine, Jay. And you can see how we progressed the number of cycles over the years. Out at 300 watt-hours per kilogram. Over here, we're now at 350. As of today, I think we've got over 800 cycles out of this at 350 watt-hours per kilogram. And we've got roughly 100 cycles now out at 400 watt-hours per kilogram. And I should emphasize these are real energy densities. So these are the cells we use. We weigh the cells. We energy got in and out. So be very wary when you see data in the literature. It quite often only consider the active materials. So this is where we stand. We expect to go quite a bit further and better. This project extended for a second 5 years. So we're now going after 500 watt-hours per kilogram. Again, using these layered oxides, but also using a much lower cost and higher energy density system in principle, and that is lithium sulfur. So sulfur is essentially free. Lithium sulfur will today give you about 400 watt-hours per kilogram volumetric energy density, but there's serious technical sulfur is an outstanding ionic and electronic insulator, so it's difficult to get materials to react. Step is used, as I said, all the material. One of the things we've discovered with these layered oxides, and this is a typical cycling curve. First cycle, you charge it up to about 4.3 volts, you discharge it, and you never get back all the capacity you had to begin with. And this is known as the first cycle loss. If we can recover that, then we should be able to get above 400 watt hours per with these materials. We believe this is due to slow lithium indiffusion at high lithium contents. And in fact, we measured this. And here's the lithium diffusion coefficient here. It's about 10 to the minus 9 centimeters squared per second until we've got about 75, 80% of the lithium in. Then it falls off the cliff, dropping by over 3 orders of magnitude. We now know that this is due to what mechanism. So for a lithium ion to jump in this lattice from this point to this point, it needs 2 vacancies. There are these vacancies as you fill the lattice. And you can think about a lecture theatre. If you're sitting in a lecture theatre now, if that lecture theatre is 75% full of people, then if somebody else comes in, everybody has to move because invariably the empty seats are in the middle. So it's a very similar thing. And taking the lithium out, there's no problem. The diffusion coefficient is the same until the last. So the same analogy with a lecture hall, at the end of the talk, everybody just flows out. So we're trying to solve that, doing some modification of the materials so we can reduce this first capacity loss. We've reduced it by more than 50% at the moment. We think we can get it even lower. But there's a number of materials, as I mentioned at the beginning. We would like to have batteries that will last 1 million miles or so. If they'll last that long, then we can hook up our cars to the grid at all times when they're actually moving. So this will give smoothing of the grid. It will allow you to have a when the grid goes down. So be more resilient. So if there's a fire and the utility turns off the power, you will still potentially have power in your house. So the way to do this is to make the materials less reactive. That means we need lower surface area, so there's less side reactions. And we go back historically looking at past. Initially, at the Exxon TIS2, we used these. These are polygons, long and about thick. When Stanley was making lithium cobalt oxide, they also used this particular picture is from Jeff Don. Sony actually used single crystals of above 10 microns in size, again, to reduce the side reactions and to make their Walkman players and so on somewhat safer. But to increase the power, commercial cells today have these meatballs, much smaller particles. I said these are primary particles are 100 to 200 nanometers, because about 10 microns. So fairly large surface area. So what the thinking is, if we go back to single crystals, yes, we'll lose some of the rate capability, but we'll have much longer lived. So Jeff Don made this 50% nickel material and speculated that it could last for 1 million miles. And I say grid, EV, interact. Issue with the meatballs, why they don't last so long. These little particles, as the lithium goes in and out, they expand and contract. So where they're wedged up against each other, they will then cause the meatball itself to crack, not the primary particles, but that large meatball. That exposes fresh electrolyte and you then get side reactions occurring on that surface. If you have single crystals, then these are not wedged against each other in the same manner, and they do not crack. And as Jay said, provided you keep their size below about 3 microns, so particles 2 microns to say 5 microns in size. And I speculate that these will be probably if we want long-lived batteries, if you want very high-powered cars, you're probably going to reduce the life and use meatball type morphology. Now, what is the optimum morphology of these materials? You can see this is really the layered compounds, which all these are. The diffusion is into the edges of these crystals, not through the flat plane. So this is not the ideal morphology. So we want to find out what the ideal morphology is. And these are some of Jay's single crystals that she used. And this is now 76% nickel, high nickel materials. But the other option is to go away from these oxides altogether and work on phosphates. As I said, that phosphates are more stable. They don't. So they're lower energy density, but we can probably solve part of that issue by putting 2 lithiums in. So we've been looking at these vanadial phosphates. So you got the vanadial octahedra and then the phosphate tetrahedra. These now have tunnels with lithium ion. And these tunnels are in all 3 directions, so they're not readily blocked. We are able to make these about 100 to 200 nanometers in size. These little cuboids are all the same shape. And I show you the electrochemistry on the right here. Lithium's in, so in here we're going from vanadium 5 to vanadium 4, then from vanadium 4 to vanadium 3. If you look at the black line here, this is the first time we cycle it this way, and coming back here. The purple line is the 50th time. So if anything, it's behaved cycle than on the first cycle. So we got proof of concept that we can put 2 lithium ions in a structure without damaging the structure. And in fact, this structure only expands by about 10% when you put those 2 lithium ions in. But there are still challenges here. In this region here, we see the bumps and the slopiness. This is single phase, extremely high rate in this region. But up here, this is now a 2-phase region between VO-PO4 and LiV-PO4. So this tends to be somewhat more sluggish. So we have to modify this more reactive so we can get the high rate reactions going on. So we're studying that at the moment. The other point I want to make is, I mentioned earlier, Battery 500 Consortium, there's 12 different partners in it. And that's what you need to make major breakthroughs and to make major progress. The vanadium phosphate work we did was one of the Energy Frontier Research Center consortiums. And in these consortiums, you want to have great experimentalists, you got to have theorists to guide you, and you got to have characterization experts, typically in the national labs where you've got synchrotrons, and it needs all those skills to make things work. Conclude with a few remarks that we all like to be disrupted in a positive manner. So mobile communications, this was really the birth of the lithium battery. This is where it made its breakthrough and enabled this mobile communications. And this has been mostly for the good. The second issue we've had the last 2 or 3 years is really COVID disrupted humanity. And this is mostly for the bad. But we learned a few things. I think to everyone's surprise that we could build a vaccine within about 12 months. We identified some real supply chain challenges where we globalized too much. So that's going to get reined in. And the disruption we're getting now is really climate change. So it's messing everything up. And lithium batteries can come to the rescue here. as I said at the beginning, we are going to have to, but it's best if we're on the active controlling side, that we're controlling what happens. And we as scientists can overcome some of these challenges. We can generate some solutions. And for all the students listening, I advise you, enjoy your research, do what you like doing, do something new, and be willing to take risks. Don't be too conservative. If you're too conservative, you won't make breakthroughs. Thank you very much, and I'll stop there.
Thank you very much, Professor Whittingham, for the very interesting and informative talk. We have several questions, and I will try to go through some of them and probably couple some of them. The first one was, you mentioned that, Singapore has the perfect weather for lithium-ion batteries or for electric cars in general. So some of our audience would like to know, what do you mean precisely by that when you say Singapore has a weather that electric car likes? Could you elaborate, please?
Yes. So lithium batteries like operating under exactly the same conditions as we humans do. So they're happy, and I don't know how to put it in centigrade terms, but in Fahrenheit terms, between about 45 degrees and 90 degrees Fahrenheit. So they don't work very well in very cold climates, and they don't work very well in hot climates like Arizona. Yep. So California is a great place to do it. And I think climate never gets very cold, and then never may get humid, but it doesn't get super hot.
Thanks, Professor Whittingham. The other questions are all more towards the notion that as we have more and more renewables in our power supply chain, we see an emerging demand for high capacity energy storage and batteries. So I'm coupling few questions here to see, get your view on which do you think are the promising batteries of the future? What about other options like hydrogen? Your thoughts on that?
Let me just say, hydrogen will work if you can make hydrogen green. Most of the hydrogen is now made from fossil fuels, oil and things like that. That's just not acceptable. And in addition, the of making the hydrogen, it's got to be energy efficient. So there's a number of challenges there. And particularly when we've looked at it for cars in say, smallish cars, it doesn't make too much sense because the hydrogen infrastructure is not really there. It costs a lot of money to put a hydrogen recharging station in place. But it's ideal, I would say, for large trucks, fleet vehicles, where you can have a hydrogen charging station at the central. Or you can have them on major highways where trucks would refuel. Batteries are not going to work for very large trucks. The challenge with any other batteries have got so low cost, it's going to be very difficult for other batteries to break into the market without them finding a high cost initial market to test, and then they can reduce their cost. But no, so at some point, none of the air systems I think are viable. For very large grid storage, maybe some flow batteries, but any flow system, you need professional folks there all the time to watch over them because they've got pumps running, corrosion issues, and so on. So it'll take time for anything else to. Lead acid storage is gone now, being phased out for lithium ion.
Great. Thanks, Prof. Whittingham. A follow-up, several members of our audience would like to know your opinion on biofuel as an alternative clean energy, because the carbon emission is sort of offset by the carbon sequestration of the plant ingredients. So few of them would like to know your opinion on this.
I think it's a little phony. Britain is importing huge amount of wood pellets from the United States. I think that's green. But my understanding, burning wood is worse than burning coal in the amount of CO2 generated. And it's not clear, people are being totally honest when they do the full cycle of CO2 capture than CO2. So biofuels, we might as well use them, but I'm not sure we should deliberately. What I'd like to see is people like to have more ethanol in the fuel, maybe from corn and things like that. So what we'd ideally like is come up with that will work with ethanol. And that's a real challenge because we've got to break that carbon-carbon bond. But that would be much cleaner.
Yep, great, thanks. This is also a question from several people. When do you think solid-state lithium-ion batteries or solid-state lithium batteries can be successfully developed? What's the biggest technical problem of solid-state batteries? Is it the interface or the ionic conductivity?
All of those things. I think you have to remember solid-state batteries are commercial now. Blue Solutions in France makes the lithium, polyethylene oxide, solid electrolyte, lithium iron phosphate batteries. They're used in little cars that you can rent by the hour in Paris. The Mercedes bus I showed you, that has, but they had a fire recently, so it's not clear if you use an organic, even if it's a polymer, that it's won't burn. So the interfaces, if any of the components expand or contract, you may break that interface. The challenge the battery industry is worried about is how much will it cost to make them compared with today's lithium ion? Mm-hmm. And my suspicion is you're going to find them getting put into things like smart watches, phones, as a kind of test bed before you see them into large, say, electric vehicles. Maybe medical sensors, things like that, where we can try them out, make sure they do work. But they're going to happen. It's just a matter of how long it will take.
Thanks, Prof Whittingham. The next question is really the environmental concerns of older generation batteries. I presume they're referring to the cobalt in the handphone batteries and also EV batteries. How serious do you think would that be, and how can we circumvent such issues?
We got to change human attitudes. Where I live in New York State, it's illegal to throw batteries into the trash, but people do. We have the largest recycling facility for lithium batteries about 100 miles from where I live. It's operated by a Canadian company. And they say they can't, in fact, get enough batteries so that it's operating profitably. The cobalt is worth a lot of money. The nickel's worth money. And the copper current collectors are worth money. So they're in operation. There's operations in Europe, in Belgium. Apple has their own system going. And I'd be very surprised if most Asian countries don't have battery recycling. That's going to be a major source of nickel and cobalt and copper for future batteries. It's going to happen. We just have to stop people from tossing their old batteries. And as I tell them, if you've got batteries in your closet, recycle them before they catch fire or something goes wrong. But no, there are recycling facilities in countries in the world now, and the recyclers will happily take your old batteries.
True, agreed on that. Switching gear, I have a question a bit more non-technical. As a student would like to would like you to share your graduate student mentoring style, if you're open to sharing, Professor Whittingham.
Yeah, my style is really to let them do their own thing. I do not treat them as technicians. No, we're paid by the federal government in the United States under contracts. So within the defines of those contracts, to do. but I do not lead them, as we say, by the nose. This is what you can do, that's what you can do. I let them do their own thing and learn, but we're all there to help each other. So as I say, we work in consortiums. My graduate students talk to graduate students on the other campuses, labs. So we tend to work as teams, and we have group meetings where only the students are there. So they don't get embarrassed if they make a mistake. So they always work with profs there. What happens if I say something silly? We say, we won't be there for some of these meetings so they can interact with each other. And no, I think that tends to be the general style. I know some people say that's not my style. I learned at Oxford, my advisor went on sabbatical, left me alone to do it. It worked out well. I went to Stanford. My advisor left for years. I basically ran his group for 2 years. And latest students, you got to do what you love doing. Do something different, do something new. Don't just follow what everybody else is doing.
Thanks for the advice. I'm sure the students will definitely benefit. Just one other question is, electric vehicles do not directly emit CO2 as we know, but they require electricity for manufacturing and charging. So I guess in total, well to wheel, how much do you think the widespread use of EVs will improve climate change?
It all depends where the electricity.
True.
So if the electricity is green, in other words, if it comes from solar or wind, it should be good. But if the electricity comes from burning fossil fuels, it's going to help. But I know in places like Australia where they ship all the good and to Asia, then burn the dirty coal in Australia itself, it's going to make the situation, in fact, worse. So you've got to use clean electricity.
Yep. There's one more question, Prof Whittingham, if I can. We start to hear about quantum batteries using superabsorption phenomenon. What do you think about this technology? Is it again a way to use the fashion word quantum?
I think you're probably right. It's probably it's in fashion. There's money there, so they're going to use it. But I tell everybody when asked, 90% of what you read in the battery area is hype. So don't believe it. Really be critical when you read something and see if it makes sense.
Agreed, Professor Whittingham. So that's all the time we have. We have a lot more questions. I would like to take the time to thank Professor Whittingham again for the fantastic eye-opening lecture on lithium-ion batteries and for the great discussion. Thank you all.
Thank you.